Okay. Well, hope you all had a good weekend. And we have another week here. This is what, week 11, I think. So we're getting along almost to the end. So announcements. Homework 6, I've moved it from this Friday to a week from today. So next Monday. Not too unexpected there. And exam 2 is scheduled for a week from Friday, and I don't anticipate moving that. That one's pretty locked in. Exam 2 will be on lessons 4, 5, and 6. So as long as we get through homework 6 by early next week, the exam's still good for that date. And it'll be just like last time, 24-hour period. It's the same kind of exam that I give during normal semesters, so it's intended to be done over a 50-minute span, but I'm giving you 24 hours to do it because of COVID. And again, just on the new material, lessons 4, 5, and 6, but otherwise it should be similar in format. The questions should be similar to the questions you've seen in the homework, maybe about 1/3 math, 2/3 concept, just like the first exam. It won't be, the first exam, you don't know what to expect. Now you do know what to expect, and I'm just saying I'm not going to deviate from that expectation. So questions about any of that? Okay, I'm sure we'll talk more about the exam as we get closer to it. Let's take a look at the warm-up question. So last time I ended up talking about the atmospheric layers, and I only got through the first one, the troposphere. And I'm sorry, I have, so you know what you're looking at here. This was kind of hard to read, so I just put the figure over top of it. So you know what's under here, you're not missing anything. Last time I talked about the troposphere. I haven't gotten to the other layers yet, but you have enough information that you can answer this. We do have these 4 atmospheric layers: troposphere, stratosphere, mesosphere, and ionosphere. And in this plot, I show the temperature profile as you go through these different layers. And some of them it's hot below and cold above, and some it's cold below and hot above. That's kind of a key thing here. So given what we said about convection, how it works, which of these 4 layers, and select all that apply, so it's not necessarily just one, merge your answers and submit them. I'll give you another 30 seconds or so to think it through. Okay, let's see how we're doing. Show the values here. So a lot of you said 1, and that's of course the only one we talked about last time. And I did emphasize there is convection going on in the troposphere. It's responsible for the weather and the jet stream and all sorts of stuff. Convection plus the Coriolis force creates our global weather pattern down in the troposphere where we live. But there's actually another layer. And again, we haven't gotten to the other layers. But there are a couple criteria for convection. I'll mention one. I'll see if you can remember the other. So if you're going to have a layer, whether it's in the interior or in the atmosphere, doesn't matter. To be convective, it can't be solid, first of all. It has to be able to move. So either a fluid layer, usually the term fluid can refer to either something in the liquid state or the gas state. It's kind of a catch-all term, at least scientifically. Colloquially, we think of fluid as liquid, but scientifically, fluid means liquid or gas. So it has to be in a state where it can move. That makes sense. But there's one other criteria for being convective, and it has to do with the temperature and temperature profile. Anyone want to shout out what that is? To have convection, what's the deal with temperature? Don't be shy.
There has to be a difference.
Yep. And so what kind of difference?
A hot and cold difference.
Yep. Hot and cold. So is the hot above or below?
Well, it's switching between above and below, correct?
Um, the gas as it moves, it will start out one below and then it moves to the other above. But overall in the atmosphere, which one needs to be below? The hot or the cold?
The cold.
No, it's the other way around.
Oh,
So no, that's okay. So
okay.
if it's warm below, and that's what we have in the troposphere, you can see the temperature profile. If it's warm below, what that does is it takes the gas, and since it's warm, it will expand. And when it expands, its density is lower, and lower density things rise. And once it gets up to the cold regions, then it's cold again and contracts. It releases its energy to the higher levels and contracts. And then since it contracted, it's higher density and it sinks. And this is the same concept as differentiation that we saw, that high density things sink. Think back to the example with the golf balls, where I had the heavy regular golf balls in pink and the wiffle golf balls in white. The higher density ones sink as long as it's a fluid medium. If it's a solid, nothing can move. So those are the two criteria. And without showing the answer, I'll just show the criteria. Oops, 1 second here. Convection occurs whenever a layer is fluid, meaning liquid or gas, and warmer below, cooler above. So given that, and given this, what's the other layer that's also convective? Someone shout it out.
The mesosphere?
That's right, the mesosphere. The stratosphere, we can see the temperature profiles inverted. There's a reason for that, and we'll get to it. But yeah, the other layer is the mesosphere. Now, yeah, the gas is moving in convective cycles up there, but it's more of a technicality. There's just so little gas up there, so little atmosphere. If you look on this axis, you can see the pressure. And so here's 1 atmospheric pressure. By the time you're up here to the beginning of the mesosphere, it's 1,000th. By the time you're near the end, it's 1,000,000th. So the densities there are just minuscule. There's hardly anything there, but what is there is convecting. Okay, good. Yeah, we didn't get to all these layers last time, but we did talk about convection, and now hopefully that's drilled in. So let's talk about some of these other layers. I'll move this over here. Okay, so we talked about the troposphere, which is the layer in which we live. It goes up to about 12 kilometers. It's convective. There's also Coriolis forces because of Earth's rotation that stretches it into this global weather pattern. But then above that, we have the stratosphere. Oops, an A, stratosphere. And this goes up to about 45 kilometers. And the defining characteristic is the ozone layer. Oxygen that we breathe is O2. Ozone, as we talked about last time, is O3. And it also forms in these biological processes. Plants, they take in carbon dioxide and release oxygen, but you also get some ozone out, and it floats up and kind of accumulates in the stratosphere. And what's really great about it for life is it absorbs high energy light coming in from the sun, ultraviolet radiation for the most part, and some small amount of higher energy stuff as well. Without the ozone layer, this high energy radiation would make it down to Earth and would strike us, and cancer rates would go up, and it would be harder for life to exist on the surface. Before we had an ozone layer, life developed in the oceans. Once we got one, life moved out on land. So it absorbs this energy from the sun, and that explains the inverted temperature profile. That light is coming down and it's being absorbed by ozone up here in the stratosphere, the upper stratosphere. And so it warms the upper stratosphere. And that's why it's cooler below and warmer above in the stratosphere. And given that, we won't have convection. The stratosphere would be really smooth, not very turbulent. Again, airplanes, they try to get above as much of the troposphere as possible for long journeys because of all that convection and the Coriolis forces, and you have all sorts of turbulence. The stratosphere doesn't have that. It's pretty smooth sailing up there. Now, let's write down the reaction that's taking place. We have O3, and it's being struck by light coming from the sun. That's the symbol for a photon. It usually refers to a gamma ray, but it can be any type of light, even ultraviolet light. And what it does is it provides enough energy to break off, break off one of those oxygen atoms, leaving you with regular diatomic oxygen, which is what we breathe and make use of. And then you have an O floating around. And these single oxygen atoms, they don't like being by themselves. So suppose you have another reaction that happens kind of right next to it. Then these O2 will find each other. These two O's will find each other and merge into O2. So that's what's happening in the ozone layer. And you may think, well, if this continues, we'll run out of ozone. But it's being replenished by the biological processes here on Earth. And there's some natural equilibrium where the sun is taking some out, and plants and whatnot are putting more into the system, and it has a natural balance. Now, that's the natural balance, but that balance can be disrupted, and we have done that by putting chlorofluorocarbons, CFCs, into the atmosphere. And CFCs, they are detrimental to ozone. They break up a lot of the ozone and resulted in the ozone hole. Now, a lot of people confuse this with global warming, and it's a completely different problem. And it's a problem that's mostly solved. This is a problem that arose in the 70s, 80s, and 90s, and we decided to do something about it, and it's mostly solved now. It'll take some time for the ozone layer to heal, but it's completely separate from global warming. It's a much easier problem to solve because CFCs, these chlorofluorocarbons, they weren't used very broadly. They're used in aerosols and dry cleaning and coolant for air conditioning and refrigerators, but not much else. And so it's a very small sliver of the global economy that was making use of CFCs. And there are other things that you can use. They're a little bit more expensive, but it doesn't like damage or threaten the entire economy, just a small sliver. And so beginning in the 90s, we started legislating the end of CFC use. And let me hop forward in the slides a little bit. I'll come back to that. Here you can see a chart. The US was the biggest culprit. We were producing the most of these, but by 1996, we had finished and weren't using them at all. And most of other countries also ended in the 90s as well. We see China and India continue to use it, but they're still ramping down their levels, or they've begun to ramp down their levels. And this plot only goes out to 2005. That's 15 years ago. So things have continued to get much better, even in these countries that didn't have that kind of regulation. So we were able to end it. And let me just show you the effect that it has. Maybe I'll write it down first, and then I'll show you some of those pictures I skipped over. So CFCs, chlorofluorocarbons, basically you have a CFC and it gets struck by high energy radiation, and one chlorine atom breaks off. That's the chloro in chlorofluorocarbon, the Cl. So the rest of it, maybe that's just called FC, but the chlorine breaks off, and once it breaks off, it can act as a catalyst. It can enter reactions with O3, and basically one free Cl floating up there in the stratosphere can destroy about 100,000 ozone molecules before it finally works its way back down to the ground or merges with something else. So they're incredibly destructive, not the CFCs, but the free chlorines, and that's where they came from. And you can see the impact. Let me go back a couple slides. The impact is primarily over Antarctica, fortunately. And the reason for that is these reactions with the chlorofluorocarbons and the chlorine taking out the ozone, they have higher reaction rates at particular temperatures and cooler temperatures. And so they're, the cooler parts of the world are more likely to have this problem. Combine that with global circulation. Most of these CFCs are not being produced over Antarctica. Were being produced over countries like our own. The global circulation would push them eventually to the polar regions, and you combine that with the cold temperatures, and it opened up these holes. And they're kind of seasonal, and as the temperature changed, they'd get bigger and smaller. But here you can see the difference. Here are two images, or two measures of this taken decades apart, one in 1979 and one in 2003, and you can see how big the problem became. And these are both taken at the kind of the same time of year when they have a big impact. But it's starting to close now since people aren't using it anymore. And it will take most of the rest of the century to replenish the ozone through the natural processes and get back to where we were. But it's happening, and so it'll be fine. And fortunately, the bad zone was over Antarctica, where there are very few people anyway, a few scientists working short-term shifts, basically. Okay, so an example of a global atmospheric problem that was solvable, and we have, for the most part, solved it. Now, again, global warming is driven by the burning of fossil fuels, putting up carbon dioxide. And that's a tougher problem to solve because so much of the global economy is based on the burning of fossil fuels. So think of the ozone hole as a little warm-up for the bigger problem that we have yet to solve. But we'll come back to that. Let's move on to the next atmospheric layer, which is the mesosphere. The mesosphere, there's not much going on. It goes up to 80 kilometers. This over on the side here. Goes up to about 80 kilometers. Again, the temperature profile is going the right way, so you have convection, but there's just very little material there, very low density. Not much else to talk about. And then you get up to the ionosphere. And this goes, up. I don't think it really has a well-defined upper limit. 100 kilometers here, this is the so-called legal definition of space. If you want to be considered an astronaut, you have to pass this boundary to get your astronaut wings. But it's kind of arbitrary, but it's getting very space-like up there. And the key property of the ionosphere, well, we kind of encountered this before. Here's the plot showing the transparency of the atmosphere, what light makes it through and what light doesn't. And you may remember back out here in the radio, the very long wavelength radio doesn't make it through the atmosphere because it bounces off the top of the atmosphere and it's bouncing off the ionosphere. And that's because the ionosphere is charged. You have charged particles floating through space. They strike the atmosphere and they charge it up in that upper layer. And that makes it such that radio waves bounce more easily. And it's actually kind of interesting. You have two layers, one or two layers, depending on whether it's night or day. You can see this line right here, this curve, that's the normal ionospheric boundary. That's the charged particles coming in from space, creating an ionized layer. During the daytime, the sun's out, and that also is producing energetic radiation and particles, and that will ionize another layer a little bit lower down. And so this has an impact on long wavelength radiation, both coming in, if it's trying to come in, it just bounces off this layer. But also if we produce it down here on the surface, you get some interesting effects. This is something that most people knew about when I was a kid, but probably none of you know about now, because none of you listen to AM radio. It still exists. There's still AM radio, but there's not much on it. It's like, sometimes it's the only radio you can get in rural areas. You can drive through vast wastelands of 1980s radio, basically. But maybe you listen to it for sports radio, but most people don't listen to it anymore. AM radio, it's a long wavelength, and there are transmitters all over the place. And these transmitters, for the most part, they're pointing down. They're trying to serve people down on the ground around the transmitter. Though some of it, it transmits in all directions, so some of it goes up. And during the daytime, it gets caught between those two ionospheric layers and just kind of dissipates. But at nighttime, there's only one layer, so it goes up and it bounces off and comes down a tremendous distance away. So if you play around with AM radio, and when I was a kid, we all had these clock radios next to our beds, AM, FM clock radios. And so at night when I was supposed to be sleeping, but I'm awake, instead I'm, tuning the AM radio, because you can pick up cities much, much farther away at night because of this bouncing effect. You can listen to baseball games far away and things like that. Again, remember, we didn't have the internet or anything, and I grew up in a pretty low density area, so it was AM radio. We eventually got FM too, but anyway, that's the ionosphere. Okay, so that's it for atmospheric layers. Questions about any of that? Okay, so next, slightly different topic. We're going to talk about temperatures. And we don't need this slide yet. Let me make this big. So Earth's temperature and I'm going to do a derivation. I think there's only like one or two times during the course I'm doing a full-blown derivation. You're not, of course, you're not going to be required to repeat this derivation, but it's good to see where these equations come from, that all the steps are kind of logical. And this one involves a lot of things that you've already seen. And we'll get out of this actually two equations for calculating temperatures of worlds. And that can be a planet, it can be a moon, it can be an asteroid, it can be a speck of dust in space. The size really doesn't matter. And it's actually a minimum. I'm not going to take into account the effect of greenhouse gases, which can boost you above what we'll derive. And so we'll talk about that separately. But yeah, let's do this derivation. So it starts with a conservation principle. Energy in equals energy out. This is a pretty reasonable starting assumption. If more energy was coming in than was leaving a world such as Earth, Earth's temperature would just keep increasing and increasing, eventually would be infinitely hot. Or if more energy was going out than was coming in, we would drop down to absolute zero. So it's probably reasonable to assume that we have established some kind of equilibrium where as much energy leaves as is coming in. Okay. Now the energy that's coming in, let's try to break that down into a few pieces. And I'll start with words and then we'll switch over to symbols. And again, you're not responsible for the derivation, but I want you to see where some of the stuff comes from. And the equation we're deriving, the temperature equation, is not in the textbook. It should be, because it's super useful. We'll use it for the rest of the semester. But anyway, the energy, the primary energy source is, of course, the sun. So we'll start with the luminosity of the sun. That's energy per unit time. And the sun's producing a tremendous amount of energy, but it's not all striking the Earth. Most of it's going in other directions. I'll just put this back up again. And we'll come back and use this in just a second. But it's emitting its energy in all directions. Only a very small fraction is hitting the Earth here. And so we're going to want to multiply the luminosity of the sun by the fraction that hits the Earth. That reduces it tremendously. And just because the light strikes the Earth doesn't mean it sticks around. Some light that strikes the Earth bounces off. And so we only want the part that's absorbed or not reflected. So we're going to multiply by the fraction not reflected. Okay, that's the energy that makes it all the way to the surface. Now on the energy outside, Earth has temperature, so it's emitting as a black body. So it has a luminosity. It's nothing we see because we see in the visible band. Given the Earth's temperature, it's emitting most of its radiation in the infrared, just as you are and the objects in the room around you. Given these kinds of planetary surface temperatures, atmospheric temperatures, most of that comes out in the infrared. But it's still a luminosity. So the luminosity of Earth, and again, this is going to be in energy per unit time. Okay, let's fill in some of these things here. Actually, let's expand this one a little bit first. So Earth, I said it's emitting as a black body. And so if we want to know how much energy is coming out per unit time, per unit area, we have a law for that. Anyone remember what it's called? Back from lesson 3? We had 2 laws about black bodies. It's one of the 2. One told us where the peak of the black body was, and one told us how much energy comes out overall. That's the one we're interested in. Begins with a W, and it's Wien's law. No, sorry, doesn't. It's Stefan's law. It's the other one. Stefan's law. And that basically is telling you how much energy is emitted per unit time, per unit surface area. So we then have to multiply by the area. If here we're starting with luminosity and energy per time, we're going to break that as energy per time per unit area, multiply by the area. And this part right here is given by Stefan's law. Okay. Well, let's fill in some symbols for all this stuff. Luminosity of the sun. The symbol is L with the little sun symbol. And that's a known value. We know the luminosity of the sun, how much energy per unit time is coming off the sun. You want to multiply by the fraction of that light that hits the Earth. Again, this is the relevant figure. Imagine the energy emitting from the sun over the course of 1 second. It will expand out farther and farther, and after about 8 minutes, it will strike the Earth. It'll be this big sphere that strikes the Earth. And the fraction that hits us is the area of the Earth, just the circle, the cross-sectional area of the Earth, divided by the area of the sphere. And so that will be pi times the radius of Earth squared. That's the collecting area of the Earth. And then the area that that light from the sun is distributed over, the area of a sphere, is 4 pi times the distance between us and the sun. That's the radius of that sphere squared. That's the fraction of the sun's light that strikes us. And then the fraction not reflected, that's just 1 minus the fraction reflected. And that fraction reflected is something we call the albedo, A. And for Earth, it's about 0.3. 30% of the light that strikes the Earth bounces back into space, mostly bouncing off clouds and the polar ice caps. They're white and very reflective. And on this side, Stefan's law is, you probably remember, proportional to temperature to the 4th power. Remember, we've had these problems if something's twice as hot, how much more energy do you get? 16 times as much. And the proportionality constant is this, at sigma, it's the Stefan-Boltzmann constant. And then you multiply by the surface area of the Earth. And so the whole Earth is emitting, and its area, being a sphere, is 4 pi times its radius squared. Okay, we can simplify this now. We can solve it. Well, first, one simplifying factor is the radius squared and the radius squared cancels out. It doesn't matter how big the world is. If it's a big world, small world, the size of the world doesn't matter. It cancels out. So if we solve for temperature, this would be the average temperature. You can group all this stuff together. (16 pi sigma). It's supposed to be a d. Whole thing to the 1/4. And the solar constant, Stefan-Boltzmann constant, pi. I'm going to plug all that in for you. And so you have this equation here, 278 Kelvin times 1 minus the albedo to the 1/4 power times the distance from the sun measured in AU. I've converted it to AU to the minus 1/2. So this is one of our two equations. And it applies, I didn't say this before, but it applies to worlds where the temperature is pretty uniform. If the temperature is uniform across the whole world, you emit over the entire area. And once you do that, you get this equation. All that you need to know is how far is it from the sun, what is its reflectivity, and you can calculate the average equilibrium temperature for that world. Now, I should point out there's a second case. Let me put that up here. Well, there are a couple different cases. To get a uniform temperature, there are two ways you can do it. One is rapid rotation. And fortunately, most of the worlds in the solar system rotate once a day or faster, or once a month or slower. So it evenly divides into two categories. Once a day or faster is rapid rotation. And if you're a rapidly rotating body, there's not enough time for one side to get too much hotter than the other. Like the Earth is rapidly rotating. Yeah, our sun-facing side is a little bit warmer, and the night side is a little bit cooler. But compared to absolute zero, it's a very small temperature change. And the Kelvin scale is measured with respect to absolute zero. So a rapidly rotating world maintains a pretty uniform temperature. There's not enough time for one side to get too hot or too cold. And then you have worlds that may not be rapidly rotating. Venus is a good example, but it has a thick atmosphere. And that thick atmosphere can carry temperature from one side to the other, maintaining a uniform temperature. So Venus, very slowly rotating, one side always facing the sun, or for long, long periods of time, months on end facing the sun, you'd expect that side to get really hot, but the atmosphere carries that heat to all other points. The poles, the equator, the daytime side, the nighttime side on Venus, it's all exactly the same temperature to a fraction of a Kelvin. So if either of those things are true, then you use this equation. Now, if neither of those are true, if it's slowly rotating and there's no atmosphere to redistribute the heat, you'll end up with a hot spot. And we call it the subsolar spot. It's the spot right under the sun. It will get hotter and the rest of the planet will get colder. And in this case, it's difficult to calculate the average temperature. It depends on how quickly heat can move through rock and metal, and it's tricky. But what's easy to calculate is the temperature of the subsolar spot. We could do this derivation just for that spot. So if we come back here, instead of thinking about the whole planet absorbing the light, let's just think about the area of that little spot absorbing the light. And instead of thinking about the whole planet emitting the light, we just think about the area of that little spot emitting the light. And they cancel out. And you get what we call the subsolar temperature equation. It's very similar, just a factor of 4 difference. And out here you get 393 Kelvin, and the rest is the same. 1 minus the albedo to the 1/4 power, distance from the sun in astronomical units to the minus 1/2. So two temperature equations, and it depends upon the context. So let's give it a practice here. I'm going to give you another of our warm-up problems. And I'll give you the one case now and the other case at the beginning of the next class. So I'm going to reset this here and give you a chance to practice this kind of calculation. And I'll expose the equation in just a second. But consider a rapidly rotating asteroid near the Earth. It reflects only 10% of incoming light back into space. So I've told you it's rapidly rotating. That tells you which equation to use. I've given you the albedo. 10% is reflected back into space. And I haven't explicitly given the distance from the sun, but you can figure it out because I said it's near Earth, and we know how far Earth is from the sun. So given this, go ahead and take in the better part of a minute. You can't really do both at the same time. The first equation is the average temperature. I'll just block that little bit. There we go. Okay, I'll make it big so you can see it. Go ahead and give that a try. You'll see lots of these, so make use of the opportunity to practice. Tricky part is the fractional powers. You can get calculator errors if you're not careful there. Give you another 20 seconds. Well, you can keep submitting. Let's take a peek at what we have so far. This is looking pretty good. Yeah, so most of you put in 271, which is the correct answer. Let me show you how we came up with that. So since it's rapidly rotating, we're using the first equation. We're getting a temperature that works everywhere on the surface. And so that's the one with 278 Kelvin. 1 minus the albedo to the quarter power, distance from the sun measured in AU to the -1/2. So the albedo is 10%. So that's going to be 0.1. You put that there. And the distance from the sun, since it's near the Earth, it's also 1 AU from the sun. So in this case, this whole last factor disappears. 1 to any power is just 1. That simplifies this particular calculation, though sometimes, we'll be closer or farther from the sun when we do this. So 1 minus 0.1 is 0.9. So it's just going to be 278 times 0.9 to the 1/4 power. And you got to remember to put parentheses around that 1/4 when you raise it to that power. And that gives you 271. Okay. So just to wrap this up and connect it to what we're going to talk about next time, I've kind of already hinted at this. These are kind of lower limits. It can be greater than this depending upon what's going on in the atmosphere. To see that, let's apply this to Earth. We use the average temperature equation applied to Earth. That's the symbol for Earth. You plug in 0.3 for the albedo. It's also 1 AU from the sun, and you get 254 Kelvin. Now, we're not all super in tune with the Kelvin scale. We don't really know, is that hot? Is that cold? So you can subtract off 273 to put it in Celsius. In this case, you get minus 23 Celsius, or 277, I guess. That's what I subtracted off. And can convert that to Fahrenheit, and that's minus 2 degrees Fahrenheit. And that feels a little cold for the average temperature of the Earth. Think of the average temperature, it's, where we're located, we're not at the pole, we're not at the equator, we're kind of in between. So our daily temperature should be pretty close to the average. And our average daily temperature is at minus 2 degrees Fahrenheit. So this is off. If you actually measure the average temperature of the Earth, the true value is about 59 degrees Fahrenheit. So we're off by about 60 degrees. And that is the greenhouse effect. And we'll see that many worlds have a greenhouse effect. Some have a runaway greenhouse effect. Some have a runaway reverse greenhouse effect. It turned itself off completely, in which case these temperature equations give the correct answer. Now, we read a lot about the greenhouse effect. We hear about it in the news, and it has a negative connotation. And indeed, parts of the greenhouse effect are bad, at least in the modern day. But for the most part, it's a natural effect caused by primarily water vapor, water suspended in the atmosphere, but also carbon dioxide and methane and a few other things up in the atmosphere. There are naturally occurring levels of these. And and it's good. It's good. It warms us by the difference here, about 60, 61 degrees, the naturally occurring greenhouse effect. If it wasn't for that, we'd be under 3 miles of ice right now. If you lowered the globe's temperature by 60 degrees Fahrenheit, where you're sitting, you probably add 3 miles of ice. So some greenhouse effect is good. The primary greenhouse effect is good. What's bad is when we mess with the natural balance and add to it. Now, fortunately, we can't put more water vapor in the atmosphere. We saturate it and it just rains back out into the rivers and oceans. But things like carbon dioxide and methane and nitrous oxide, we are increasing those levels. The carbon dioxide, just since the Industrial Revolution, we've increased the carbon dioxide in the atmosphere by 35%, and the methane by 150%, and nitrous oxide by like 15%. So we can change the levels, not of the primary greenhouse gas, the water vapor, but these secondary ones, and those will have small effects, increasing the temperature by a degree and then by another degree. And just a few degrees change in temperature can have important consequences for life, at least as we know it and what we're accustomed to. Anyway, we've hit 3:30. So we'll return to this next time and we'll talk about how the greenhouse effect works and some of the consequences, and then we'll move on to the moon. All right, thanks a lot.
Thank you.
Thank you.
You.
Thank you.
Professor Eckhart, did you write down any notes about the ionosphere?
I don't think I wrote, no, I didn't. I just described it.
Okay, like if there were a few key terms for me to write down for that, what would you say?
Long radio waves reflect off of it. That's the primary characteristic. It's charged by high energy particles from space. During the daytime, it's charged also by the sun. And because of that charging, radio waves bounce off of it, both radio waves coming in and radio waves that we transmit down here on the surface. I gave AM radios the good example of that.
So long radio waves deflect off of it.
Yep,
Okay, thank you.
sure.
Have a good one.
You too.
I just had a quick question. When it comes to like, was it like studying planets or exoplanets or anything? Do we really care, or I guess we being scientists, do they really care, like how closely you get, like what the temperature is, or are they just trying to figure out if it's like boiling or freezing?
We can figure out the orbits. That's one thing that we can do with current technology. And then we do calculations just like we went through today. Once they know there's a planet there and they know how far it is from the star, they put the luminosity of the star here. Instead of luminosity of the sun, luminosity of the star, they put the distance of the planet from the star. And for different guesses about the reflectivity, they can calculate the temperature of the planet.
Are they able to use like spectroscopy or anything to figure out like the atmospheres to see like, oh, there might be a greenhouse effect or something?
Just beginning to have that capability. Usually it's with like gas giants. If you have a really large gas planet passing in front of a star, then some of that light will go through the outer layers of the atmosphere and you'll get absorption lines, and we can start to study the atmosphere in that way.
Oh, okay. Okay, that's cool. Well, thank you.
Sure.
See ya.